Thanks, Laura, and a special thank you to you this afternoon for being alone in our booth instead of with a partner. We really appreciate Laura's work to get us all set up. As she said, this afternoon we are going to talk about 5 steps which we can use to improve our systems engineering processes. Systems engineering is absolutely critical in today's more with less environment. And the ultimate standard for an improved systems engineering process is that we can consistently hit the customer's target. This is our raison d'etre, or reason for being, to satisfy our customers. And so that's the ultimate standard by which we would judge our process and its results. We need to make our process both effective and efficient. In looking at a process to see if it's effective, we have to ask, are we doing the right things? Are we on the right track? To ask whether or not it's efficient, we ask, are we doing things right? Those are different questions, and they both have to be answered in the affirmative in order for us to have a truly effective and efficient process. This is the same kind of a test that is applied to the ultimate system solution in the validation and verification stage at the end of our process levels and at the ultimate end of our design process. When we validate a system, a solution, we ask, do we have the right system? Do we have the right solution? And then we verify that we not only have the right solution, but we have the system right. It functions the way that it needs to function. The effectiveness question is a very important one. Russell Ackoff, who was a seminal systems thinker and a professor at the Wharton School, the University of Pennsylvania, said, "We fail more often because we have the right solution to the wrong problem than because we have the wrong solution to the right problem." If you think about that, what he's saying is that we're better at getting an efficient system than we are at getting an effective one. We're more inclined to get a system that functions the way that it's designed to function, and we have problems in the area of making sure that we have the right system solution. We have to deliver value without waste. In an era of scarce resources being applied to large, complex problems, we have to be able to avoid wasting those resources. This is the goal for those of you who are knowledgeable and practitioners of the lean system. This is the goal of the lean system, is to do what we need to do without waste. In the lean principles, we learn to sort out value adding from non-value adding process steps. These 5 steps that we're going to discuss today should help us to do that with respect to systems engineering processes. What are the 5 steps that lead us toward success? They are to maintain a systems view throughout your design process, to minimize the risks, to make your practice agile and responsive, to shape your process to converge on a design solution, and to account for the system context. We'll discuss each of these in detail. Arguably, the first step is the most important one that we could possibly take. If we took no other steps, this one alone would improve our practice. Maintain a systems perspective is very, very important. How so? If you're working a puzzle, we all know how helpful it is to have the box top there ready to look at. It's critical sometimes to sorting out pieces, to knowing where they'll fit, to look at the piece and see where it goes in the ultimate design. This perspective is what allows us to make sense of our system design. And we need to keep that systems view ever before us all the way through the entire design process. How do we go about that? How do we climb this first step? Well, this means that as we work our system through the levels, and we'll talk about how we go through the levels, but as we work it through, we keep all four domains in focus. We don't work on one domain and then move to another domain and try to work them down completely. But we work in layers in order to maintain this systems view. So we begin with a high-level description of the entire system. Sometimes this is so high level that it seems simplistic. It seems like we might not be going anywhere with it. But it is critical. It is important. Secondly, as I said, we incorporate all four of the systems engineering domains at each level. Then we proceed with increasingly detailed descriptions of the system solution. That's what defines our levels, is this increase in detail or granularity. So we begin with a very, very high level, almost simplistic description of the system that we need. And we begin to flesh that out with detail to increase the granularity as we drop through the layers. And as we do so, we incorporate all four of the domains. So at every level, requirements and behavior and physical architecture and validation and verification are critical concerns. So we keep all four of those in front of us as we proceed to a more and more detailed description of the solution. We address all aspects of the model, and we hold all the domains in relationship to each other across each layer. So that at each layer, if you stopped at any given layer, you would have a complete description of the system. It might not be granular enough to become a specification from which you could build the system, but it is a complete description of the system at that level of granularity. That enables us to maintain this systems view, to keep everything in context. The second step is to minimize risks. This basically means don't create risk. Self-inflicted wounds are the worst possible wounds. Whether you're talking about a sports team that's playing a game or a design team that's designing a system, it's the problems that we bring on ourselves that are the most painful. One of the greatest source of these problems is stovepiping. That's a major source of risks. It costs us in terms of communication, and it costs us in terms of work and data loss. How does stovepiping develop? The first way that it can develop is if we try to pursue the domains one at a time all the way down to ground. This is the old waterfall development type model, where the first thing we do is we take the requirements and we analyze the requirements and we try to chase them all the way down in as much detail as we can possibly get, running the requirements to ground before we begin to talk about the system behavior. Then we talk about the system behavior, and then the physical architecture, and finally we go back and do our test and evaluation, our validation and verification. So chasing these one domain at a time is the first way that we can develop stovepipes. The second way is developing different models for each domain. In document-centered systems engineering, we develop a set of requirements documents that in essence were looked at as if they were a model of the requirements for the system. And then separately we began to develop a picture and a description of the system behavior. That became a separate model. it reflected the understanding of the people who developed the behavioral description of the requirements, but they were not a part of the same model. The same was true when you begin to translate allocate behavior into the physical architecture. Again, two separate models rather than a unitary model. And finally, we did our test activities. Once we had gotten to the end, we tested the physical architecture back against the requirements. So we used different models essentially for each domain. It's hard to tell which came first, the chicken or the egg, in specific practice, but because of this way of thinking about the separateness of the domains, separate tools have sprung up. So we have requirements tools, and we have physical architecture tools, and we have process modeling or behavior modeling tools, and we have all of the systems that we've developed to verify and validate the system. So we have separate tools. All of this contributes to a stovepiping between the domains. There's an even more subtle risk here that occurs because the team will begin to see themselves as specialists. And we all know the persons who say, I'm a requirements engineer, I'm an architect, I'm a this and I'm a that. Keep in mind that the job of systems engineering is to draw all of this together, not to create slots where we put systems engineers who work on requirements and systems engineers who work on architecture. So we're here to coordinate specialists, the component engineers, for example, and to draw the process together, not to create separate areas. What does this cost us? It costs us work and data loss. It costs us as we have to transfer information and specifications, we lose information. It costs us communication, the ability to talk back and forth. I like to think of it in terms of a football play. What you see diagrammed here is a fairly risky play. The center snaps the ball to the quarterback drops back, pitches to a back in the backfield who runs to one side or the other and then throws a pass to a wide receiver. Now, if you're looking at my pictures, if there are any Michigan fans in the audience, the picture in the lower left corner, that is a catch, by the way, for Michigan fans who watched the bowl game with my Virginia Tech Hokies. So that is Danny Cole making an actual catch. That aside, the danger with this play, what makes this play risky, is all the exchanges of the ball. Every time you exchange the ball, every time you move the ball from one player to another, you create a risk. What's the risk? Fumble, dropping it, incomplete passes, interceptions, all kinds of things can happen. We face the same kind of risk on a systems engineering team because we create data exchanges. And every time we have a data exchange, we have the same kind of risk. Every time we have to move from one model to another, from one tool to another, we create that same kind of risk. Now, for those folks who use separate tools, you'll often hear them talk about our tools are coordinated. They're designed to work together. If you talk to a college football coach, he'll tell you that his team practices together, that they coordinate, that they can pull off this kind of play because they work smoothly together. Does that mean that you have any teams that never fumble, never drop the ball, never have the ball intercepted? Of course not. One of my favorite moments from the Johnny Carson show was when he, on the eve of a bowl game, interviewed Lou Holtz, who was at Arkansas at that point. Holtz had a passing attack, and Carson asked him, he said, "Coach, you've got this passing attack going, and Woody Hayes over at Ohio State has said that when you put the ball in the air, three things can happen, and two of them are bad. How would you respond to that? Holtz thought for just a second before he shot back. Woody's talking about his receivers, not mine. That's the way that we respond when we use these multiple tools and multiple data exchanges and communication exchanges. We respond that we are talking about tools that are coordinated. We're special. We don't drop the ball. We don't drop data. But the fact remains that every time we have an exchange, every time we have an opportunity, we risk dropping data and risking our overall design. So how do we cope with this potential for drop data and miscommunication caused by the differing models? The answer is both obvious and not obvious. It's obvious in the sense that if you don't have multiple models and you don't have multiple tools, then you don't have these handoffs. You have your work seamlessly placed in one model and handled by one tool. So a single model in a single repository constructed and maintained with a single tool reduces and eliminates those handoffs. So now your work is reflected directly into the tool and the model and can be used by whoever needs to use it without the necessity of translation and interpretation. So one model, one repository, and one tool would result in fewer or essentially no handoffs and therefore fewer fumbles and gaps in the data. Step 3 calls for us to make our practice agile and responsive. Our customers live in a dynamic environment. They're called upon to make changes in the ways that they serve their customers. As their customers' requirements and needs change, then their needs change. When their needs change, the requirements for our development projects change along with them. So because our customers live in a dynamic environment, so do we. The traditional systems engineering practice is fairly rigid and unresponsive. The traditional waterfall approach, where we drill down through each domain in turn, does not handle late arising requirements very well at all. These require us to return back in the design to earlier steps, which really scrap the decisions that have been made up to that point. In response to this dynamic environment, systems like rapid spiral development have come about and have provided some answers and some responsiveness. In the software world, agile development is a response to this need for responsiveness and agility. Our practice must be responsive to the needs of our customers. It's important to remember that our customers need the system to meet their needs on the date of delivery. That's the date that they're concerned with. Requirements may change between the time that they're first cast and the project is first begun until the date of delivery. And it's that date that our customers regard as the ultimate date on which the solution will be judged against the requirements. So as requirements change or evolve or arise, the customer is interested in our being able to respond and deliver a system that responds to the requirements when we deliver it to them. How do we meet this need? We, number one, have to maintain a connection with our customers and stakeholders. They need to be involved in our process as we move through the layers. Because we get a complete system at each layer, this is relatively easy to do if we will simply make the effort to keep the stakeholders involved. The other thing to keep in mind is that the behavior domain is particularly critical to our agility. As things arise, as requirements arise, as needs change, if we look into the behavior domain, we can see how the system's behavior must change in response to that. And we can move from there to allocating behavior to architecture and making changes in the system design. If we've skipped the behavior step, or if we have somehow short-changed the behavior domain, then it becomes much more difficult for us to be agile and flexible. So understanding the behavior domain provides implementation choices that we can use to become more responsive. Our fourth step is that we need to shape our process so that we converge on a design solution. This is where the increasing granularity approach helps us. We make the decisions that we can make at any given level. So as we begin to consider one choice over another, one approach over another, we make those modifications to the system solution as we move forward. And then when we move forward, we increase the granularity, which brings up a whole new set of questions that we deal with. But this is the key to convergence. If we don't do this, we wind up with fragmented domains. We don't communicate from domain to domain, and so it becomes difficult to build the convergence, and the difficulty in building the convergence leads to a further fragmentation of the domains. This is also a good way to deal with complexity. Rather than trying to tackle the most complex description of the system at the very outset, we begin with a simpler description and build the complexity as we go. So as we drop layer to layer and increase the granularity, we not only make choices about which way we're going to go with respect to given questions, but we also deal with an increasing level of complexity along the paths that we choose to go. So we're not distracted by complexity that arises in a path that ultimately we're going to choose not to follow anyway. This allows us to make rational and intentional choices so we can feel confident that the decisions that we've made, the design trade-offs that we've made, and the design choices have been rationally based and we've made them intentionally. We are also comforted that when we get to the end, we've dealt with all the relevant issues. We're not going to get to the end and discover that we've left something hanging, because we've dealt with it in this way of increasing granularity. So how do we manage this? We begin at a high level with low granularity. We do a high level description of the system. We work forward from there. We get stepped increases in granularity and stepped increases that go with that in complexity. We make our design choices, and all the while we're able to converge on a particular solution. In step 5, we account for the operating environment. This really is a part of step 1. So we're going to come back and end where we began with the systems view. But this is a part of the systems view, and this is a critical concept. In any systems design effort, there are 3 systems. There's the system of interest. We almost never move that. We almost never miss that. We know what we're trying to design. Secondly, we have the system that we use to design that system of interest. So how we're organized. And we talked a little bit about how we organize that, and how we approach it. And then we have the system in which it'll live. It's a critical mistake to not understand fully the system in which it'll live. If we don't understand the context, then we're not really going to understand the problem. You can think of the problem as some hole or gap or issue in the context system. We're designing a solution to fill that hole, to bridge that gap. So as we put a solution into that gap, it's going to interact with the system. And we need to understand all of the ways that it'll interact, because if we're not careful, it'll interact in ways that we didn't plan and perhaps ways that we didn't want it to. So we need to control the consequences. We need all the consequences of our solution to be the ones that we intend. The failure to understand the context can lead to unintended consequences. Now, the little dude down here with the glasses is wearing a fur coat. He's there to remind us of the fur industry's famous failure to understand the environment, quite literally the environment. In the 1950s, there was a big quest to find a fur-bearing animal that produced a high-quality fur that could be produced for low cost. So basically, it needs to be an animal that'll eat whatever's available, that'll eat cheap food. It needs to be an animal that produces a high-quality fur that people would not be reluctant to wear. It needs to be an animal that's resistant to disease. It would be good if it was an animal that could live in all kinds of climates. So there was a worldwide search for such an animal. And a couple of companies found an animal in South America that met that description. It could live anywhere, it ate anything, it was very inexpensive, it was very prolific, it had lots of young, it was easy to care for, not a problem to raise, and it produced high quality fur. It was called the nutria. That's a picture of a nutria there in front of the guy, and I put that there to show you what kind of size comparison it is. Basically it's a rat, but it's the size of a small to medium sized dog. So these companies began to import and sell nutria, and initially they were introduced in the East Texas, Louisiana area, and the problem quickly became that all of the strengths of the nutria developed into problems. This is an animal that produces 20 young a year. So if you have 20 nutria and 20 breeding nutria, then at the end of the first year you're going to have 400 nutria, and then it'll just simply grow from there. So they had lots more nutria than they intended, and their prolific nature meant that they pretty quickly breached their containment. They got out into the wild. That was not a problem for them because they eat anything, they're resistant to disease, they can live in any climate. So they began to move around, to travel, to stow away, to go to different areas. They continued to be prolific, to expand their populations. And today, there's a problem out in the Blackwater Swamp on the eastern shore in Maryland because there's a population of nutria that are eating the swamp down to just stubble. It looks like a wheat field that's just been harvested where you should have a swamp, a marsh. So the nutria are a problem, and they're a problem because in terms of solving the fur-bearing problem, they were a perfect solution. But they also lived in a context system, and they've done huge levels of damage to that context system because nobody thought about that. So how do we master that? The first step is that we ought to be in the business of mapping the system context, or the context system. We need to understand that. How does that help us? Well, the first way is that it helps us to model the system boundary accurately. We know what's inside and outside. We know where we can design to and where we have to interface. We can understand and model the interfaces. We understand what the consequences are of introducing the solution. And we're able to prevent the cure from becoming worse than the disease. So if we're able to implement these 5 steps, we'll be able to improve our systems engineering practice in several important ways. To recap the 5 steps, they're to maintain a systems view throughout the design process. And this means working in layers across all of the domains in each layer, increasing the granularity from layer to layer, and keeping the systems view. We minimize risks by minimizing the number of models that we make. We minimize the number of handoffs. We promote the communication, and that keeps our project risks down. We make our practice agile and responsive. We're able to deliver to our customers and stakeholders the system that meets their needs at the point that we deliver it. We shape our process to converge on a design solution so that we're not either overwhelmed by the complexity or off chasing down one trail after another in an attempt to pick a trade-off at the highest level of complexity. And then finally, we account for the system context. So we understand the system context, and we understand it in a way that allows the intended consequences to be the only consequences. I hope this is helpful. I look forward to questions either now as you submit them through the system or as you submit them in the next several days across the website. The first question we have today is from John. John asks, how do we handle additional requirements as they are introduced after the design is already in process? John, as we are moving from layer to layer and increasing the granularity, as additional requirements appear, we can first ask ourselves, how does this impact the behavior of the system? And we already have a webbing established from requirements which are the basis of behavior, and behaviors are allocated to components, to the physical architecture. So as we look at the new requirement that's appeared, we have an idea of where it fits in the system. And then we can simply make the modifications that we need to make. We can include the requirement. We can look at its impact on other requirements, its impact on behavior, and ultimately track that out in our model. But it's very important that at any point a requirement is introduced, we have a 4-domain layer model of the system at a level of granularity, and we are simply able to analyze and incorporate that requirement. Our second question comes from Mark, who asks, would it help to model the context system even before we specified the design task? Yes, it would, and that's really important and an area that needs some exploration and that would have big dividends. Acquisition folks could use systems engineering to model the context systems around the problems that they see. If they did that, what they would discover is a better picture of the shape of the problem. So you would know more about the gap that you're trying to fill. You would know more about the interrelationships between the problem and the rest of your context system. So you could do a better job as an acquisitions person of specifying what sort of a system solution you're looking for, because you would have a better definition of the problem. Thank you for joining us today. We hope that you have enjoyed and profited by our time together, and we hope that you'll join us again soon in our continuing series of webinars presented for you by Vitech Corporation.